In this quick tutorial, we'll discuss the Fibonacci sequence and how it relates to the golden ratio. The Fibonacci sequence is the sequence that begins like this. We have 1, 1, 2, 3, 5, 8, 13, and so on. Just by looking at this, can you see how this sequence is derived? Notice that the third number in the sequence, 2, is a sum of the previous two numbers. 1 plus 1 makes 2. 3 is the sum of the previous two numbers again. 1 plus 2 makes 3. And this is how the Fibonacci sequence is born. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, and the pattern continues. Unlike regular sequences, we often label the terms in the Fibonacci sequence by f sub 1, sub 2, sub 3, and so forth, rather than the typical a sub 1, sub 2, etc. Now what's interesting about this sequence is that the ratio of successive terms approaches a fixed value known as the golden ratio. So take a look at this table right here. The numerator of each of these fractions represents the sequence of numbers in this sequence. This table is formed by taking the subsequent value in the sequence and dividing it by the previous. For example, if we divide 1 by 1, we get a quotient of 1. Dividing 2 by 1 gives us 2, 3 by 2, 1.5, 5 by 3, 1.667, and eventually, as you continue to do this, you will reach a consistent output of 1.618. That ratio is what is referred to as the golden ratio, and it's represented by the Greek letter phi. This number can be approximated by taking the square root of 5 plus 1 and dividing it by 2. Now, coupled with the golden ratio is the golden rectangle. This is a rectangle for which the ratio of length to width is equal to approximately 1.618. If that didn't make sense to you, think of a rectangle whose dimensions is approximately 1.618 to 1. Underneath here is an example of the golden rectangle. So let's say we started off with this bigger rectangle, which had the dimensions of 1.618, which spans from here to here, and from here to here, 1 unit. From this rectangle, if I were to create a square that is 1 by 1, I would end up with this rectangle. A square can also be formed out of this rectangle shown here in B, leaving us with a smaller rectangle. Again, a square can be formed out of this smaller rectangle represented as C, forming a even smaller rectangle. And the same pattern can continue within here. Interestingly, if we focus in on, let's say, square A, the distance from here to here, if I were to draw it out as a arrow, and then I used the tip of this arrow to form an arc, we would get a pattern that looks like this. Again, if I were to do the same thing for this square, where I have an arrow that extends to here, and this arrow formed an arc, the arc would continue like this. Again, I'll extend an arrow from one vertex to the other, and it would continue drawing an arc like that. Eventually, we would get a pattern that looks something like this. The reason why this is significant is because the golden ratio and the golden rectangle appear frequently in nature and in architecture and even in design. For instance, this is what you would see in nature, where it has a pattern of a swirl. And we also see this in architecture and art, as shown here. Now, what's also interesting is that we can extend this idea to making beautiful web pages. For example, here is a string of text. And notice that the line height is close together. Line height is the vertical distance between lines of text. Say we wanted to make this text a little more readable. We can actually use the golden ratio to help us out with that. For example, on your screen right now, I am editing the code in real time. And I will put the line height as 1.618. Take a look. Not only is the appearance of the text more readable, it's actually more pleasant to the eye as opposed to it being closer together. And so there you have it. A quick tutorial on the Fibonacci sequence and the golden ratio.